Trains are massive machines, often stretching for miles and carrying tons of cargo or hundreds of passengers. With such size and momentum, stopping a train is no small feat. Unlike a car, which can come to a halt within a short distance, a train requires much more time and space to slow down and stop due to its immense weight and speed. But how exactly do train brakes work? The answer lies in a combination of mechanics, physics, and advanced engineering. In this video, we're going to take an in-depth look at how train braking systems function, how they evolved over time, and why they're crucial for both safety and efficiency in railway operations. Let's explore right here on History of Simple Things. At its core, the idea behind a train's braking system is similar to that of any other vehicle. The brakes create friction to slow down and stop the train's wheels. However, unlike cars, which typically rely on hydraulic or mechanical braking systems, trains utilize air brakes as their primary method of deceleration. This system uses compressed air to engage the brakes and has become the gold standard for train operations worldwide. The basic concept is this. When the train driver, known as the engineer, pulls the brake lever, air pressure is reduced in the brake pipe, which runs the entire length of the train. This reduction in pressure causes the brake valves on each car to release air from reservoirs, applying the brakes on every wheel. The brilliance of air brakes lies in their simplicity and efficiency. They allow the engineer to control the brakes on each individual car simultaneously, ensuring even braking across the entire train. Moreover, air brakes are fail-safe. In case of an emergency, or if there's a malfunction in the system, the brakes automatically engage. This is because the brakes are applied by a drop in air pressure, meaning any loss of air will cause the brakes to kick in. Train brakes weren't always as efficient and reliable as they are today. In the early days of railroads, stopping a train was a laborious process that involved manual brakes. Each car had its own hand-operated brake, and brakemen had to run along the top of moving trains, turning brake wheels on each car. This was not only inefficient, but also incredibly dangerous, leading to numerous accidents and injuries. The invention that changed everything was the air brake, developed by George Westinghouse in 1869. Before this, trains relied on gravity and handbrakes to stop, which was neither reliable nor safe, especially for longer trains. Westinghouse's air brake system introduced the concept of using compressed air to apply brakes uniformly across all cars, drastically improving safety and control. His system was adopted by railroads across the world and remains the foundation for modern train brakes. Over time, the air brake system has been refined and improved, but the basic principles established by Westinghouse remain the same. The move from manual brakes to air brakes was a revolution in rail safety, enabling longer, heavier trains to be controlled with precision. A modern train brake system is composed of several key components that work together to slow down and stop the train. The first of these is the brake pipe, a continuous pipe running from the locomotive to the last car. The brake pipe serves as the conduit for air pressure, and its pressure level determines whether the brakes are applied or released. In normal operation, the brake pipe is charged with high-pressure air, and when the engineer reduces the pressure by applying the brakes, the system responds. Each car in the train has its own brake equipment, including an air reservoir, brake cylinder, and control valves. The air reservoir stores compressed air that's used to apply the brakes. When the brake pipe pressure is reduced, the control valve on each car opens, releasing air from the reservoir into the brake cylinder. The brake cylinder then pushes brake shoes against the train's wheels, creating friction and slowing the train down. The engineer has control over both the service brake and the emergency brake. The service brake is used for normal operations, such as gradually slowing down or stopping at stations. The emergency brake is reserved for critical situations where the train needs to stop as quickly as possible. In an emergency, the air pressure is dumped from the entire system, causing the brakes to apply at full force on every car. Because the brakes rely on air pressure, the system is inherently safe. Any failure in the air supply automatically triggers the brakes. In addition to the air brake system, many trains today are equipped with dynamic brakes, a secondary method of slowing down the train, especially in electric and diesel-electric locomotives. Dynamic braking works by using the train's electric motors in reverse. Instead of using mechanical friction to slow down the train, dynamic braking takes advantage of the train's momentum. When the dynamic brake is applied, the electric motors that normally drive the train's wheels are turned into generators. These generators convert the train's kinetic energy into electrical energy. The electrical energy is then dissipated as heat through resistors, slowing down the train. Dynamic braking is particularly useful on long downhill stretches where prolonged braking is required. It reduces wear and tear on the air brakes and provides smoother control. However, dynamic braking is not a replacement for air brakes, it's a supplement. Once the train has slowed to a certain speed, the air brakes take over to bring the train to a complete stop. Stopping a train involves significant physics, primarily because of the sheer mass and velocity involved. Trains can weigh thousands of tons and travel at high speeds, so the braking system needs to overcome a tremendous amount of inertia. Newton's first law of motion states that an object in motion will stay in motion unless acted upon by an external force. In the case of trains, that external force is the braking system, which provides the friction necessary to slow down the train. The amount of friction generated by the brakes is proportional to the pressure applied by the brake shoes onto the wheels. The heat produced by this friction is substantial, especially during prolonged braking, and can cause wear on the brake components. Engineers must balance the need for effective braking with the risk of overheating or wearing down the brakes too quickly. The braking system of a train is a marvel of engineering, combining mechanical, pneumatic, and electrical systems to safely bring these massive machines to a stop. From the invention of the air brake by George Westinghouse to the modern use of dynamic braking, train brakes have evolved to meet the increasing demands of rail transportation. Understanding how these systems work not only highlights the ingenuity behind rail technology, but also underscores the importance of safety in an industry that moves millions of people and tons of cargo every day. Next time you see a train rolling down the tracks, remember that stopping it requires more than just pulling a lever. It's the result of a complex and highly coordinated system designed to keep everyone safe. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.